Polarization. We know that light is an electromagnetic wave, that is, its electric and magnetic field vectors are perpendicular to each other and to the direction of propagation of wave. We also know that light is emitted by atoms. Thus, when one atom emits a wave along the X-ray, say its electric field, it may be along the y-axis and magnetic field will be along the z-axis. However, if another atom in the source emit a wave traveling along the x-axis, and it is not necessary that electric field be along the y-axis, it can be along any direction in yz plane. So if you want to consider, you can consider in any plane. So in the magnetic field will be along a direction of perpendicular to it. Thus, in general, electric fields of waves emitted along the x-axis by a source of light like the sun, stars or a light bulb will be in all possible directions. So in yz plane, and corresponding magnetic field will be perpendicular to the electric field. Such light is called unpolarized light. Now it is represented by double-headed arrows. So showing the direction of electric field in plane perpendicular to the direction of propagation, and this is your figure 7.61, and below that double arrow we have shown. On other hand, if somehow light is constrained so that its electric field is restricted along one particular direction, then it is called light per plane polarized light. This is shown by figure 7.6b. And for light beam traveling perpendicular to the plane of the paper. So how can we get polarized light? There are certain types of materials which allow only those light waves which have their electric field along a particular direction to pass through and block all other waves which have their electric field in other directions. These wave materials are called polarizer, and a Polaroid is a kind of synthetic plastic sheet which is used as a polarizer, so which we use in our goggles. The particular direction along which the electric field of emergent wave is originated is called polarizing axis of the polarizer. This is shown in figure 7.7a. So if you want to see, you can see here, this is colorful diagram. Thus, when unpolarized light passes through a polarizer, emergent light is plane polarized. The plane ABCD containing the electric field vector plane polarized light is called plane of vibration, while plane perpendicular to the plane of vibration, that is horizontal plane, and it is called the plane of polarization. So if polarized light is made pass through another polarizer with its polarizing axis perpendicular to the polarizing axis of the first polarizer, no light can emerge on other side, as second polarizer would allow only waves having electric field parallel to its polarizing axis to pass through. On the other hand, if the polarizing axis of second polarizer makes at an angle smaller than 90 degree with that of the first polarizer, so then the component of electric field of polarized light along the direction of light polarizing axis of second polarizer can pass through. The intensity of light will reduce after passing through each polarizer. We will mathematically calculate this below. We have used the electric field to explain the phenomenon of polarization. However, it could also explain in same manner using the magnetic field. Now consider an unpolarized wave having angular frequency omega and a wave vector k equal to 2 pi upon lambda. traveling along the x-axis, the magnitude of electric field is given by E equal to E0 sin kx minus omega t, where E0 being the amplitude of the wave. So we can see this in chapter number 13 in 11th standard book. The intensity of a wave will be proportional to mod of E square. The direction of electric field can be anywhere in y-z plane. We will consider the passage of wave through two polarizers as shown in figure 7.7b. So here you can see this term. Let us consider a particular wave having its electric field at an angle phi to the axis of the first polarizer. The component E0 cos pi will pass through the first polarizer while the normal E0 sin phi will be obstructed. The intensity of this particular wave after passing through the polarizer will be proportional to the square of amplitude, that is to the E0 cos pi mod square. For unpolarized incident wave, phi can have all values from 0 to 180 degree. Thus, to get intensity of plane polarized wave emerging from the first polarizer, we get to average E0 cos phi square over all values of phi between 0 and 180 degree. The value of the average of cos square phi is half. Hence, the intensity of wave will be proportional to the half of E0 square, and the intensity of unpolarized wave reduces by half after passing through a polarizer. Therefore, now consider the linearly polarized wave emerging from the polarizer. Let us assume that polarizer wave has its electric field E1 along y direction as shown in figure. We can write the electric field as E1 is equal to j cap E10 sin kx minus omega t, where E10 is the amplitude of this polarized wave. The intensity of polarized wave is given by I1 is proportional to the E10 of mod square. And now, if wave passes through the second polarizer, whose polarization axis makes at an angle theta, you can see here this angle will be theta, okay, in this diagram. With the y direction, only the component E10 cos theta will pass through. The amplitude of wave which passes through the say E20, now E10 cos theta, and its intensity will be I2 is proportional to the E20 square. So I2 is proportional to the E10 square cos square theta, and I2 is equal to I1 cos square theta. This is known as Mears Law after E.L. Mears, who discovered the law experimentally. Mears law gives the intensity of linearly polarized wave after it passes through a polarizer. Note that theta is the angle between the axes of polarization of two polarizers. If theta is equal to 0, that is polarization axes of two polarizers are parallel, the intensity does not change while passing through the second polarizer. If theta is 90 degree, cos square theta is 0 and no light emerges from second polarizer, that is theta equal to 0 and 90 degree are known as parallel and the cross setting of the two polarizers. So that is the explanation on the basis of this diagram. Now we can see about this polarization by reflection, and we call it as a Brewster's law. When light is incident at an angle on boundary between two transparent media having refractive indices n1 and n2, part of it gets refracted and the rest gets reflected. Let us consider unpolarized light incident from medium of refractive index n1 on such a boundary perpendicular to the plane of paper as shown in figure. So unpolarized incident ray, and on other side polarized reflected ray, partially reflected polarized reflected ray by the bottom. So incident wave is unpolarized, its electric field is in the plane perpendicular to the direction of incidence and is resolved into two components, one parallel to the plane of the paper shown by double arrows and the other perpendicular to the plane of the paper shown by dots. Both have equal magnitude. In general, reflected and refracted rays do not have equal magnitudes of two components, and hence the partially polarized, it was experimentally discovered by capital D. Okay, that is nothing but D. Brewster's in 1812, that of a particular angle of incidence theta b is shown in the figure. So this angle theta b we have shown in the figure, incident ray with this normal. The reflected wave is completely plane polarized with its electric field perpendicular to the plane of paper, while refracted ray or wave is partially polarized. This particular angle of incidence is called Brewster's angle. For this angle of incidence, the refracted and reflected rays are perpendicular to each other. From the figure, for angle of refraction theta r, theta b plus theta r is equal to 90 degree. From law of refraction, we have n1 sin theta b is equal to n2 sin theta r, with equation 7.14 gives n1 sin theta b equal to n2 sin 90 minus theta b, which will give you n2 upon n1, which is equal to tan theta b, and theta b equal to tan inverse of n2 upon n1. You can see here this derivation, so which is known as Brewster's law. This phenomenon of polarization by reflection is used to cut out glare from the reflecting surface using special sunglasses. Sunglasses are fitted with polarides which reduce the intensity of partially or fully polarized reflected light coming to the eyes from the reflecting surfaces. As seen from above, intensity of light or light coming from artificial sources which is completely unpolarized is also reduced to half of the polarized, and this phenomenon of polarization by reflection works only for non-metallic surfaces. So this is the use of polaroid, okay, and by using scattering we can see the polarization by scattering also. So when sunlight strikes air molecules or dust particles in the atmosphere, it changes its direction, is called scattering. Already this phenomenon we have studied in 11th standard also. So we see the sky as a blue because of scattering, as blue light is preferentially scattered. If there were no scattering, the sky would appear dark to us as long as we do not directly look at the sun, and we could see stars even during the day. When sunlight is scattered, it gets partially polarized in a way similar to the reflected light seen above. The degree of polarization depends on the angle of scattering, that is, angle between the direction of the light incident on the molecule or the dust particle and the direction of scattered light. If this angle is 90 degrees, scattered light is plane polarized, and the scattered lights reaching us from different direction is the sky is polarized to the different degree. So in this way, which we can see the phenomenon or polarization of light. So now which we can see on the base of that, okay, that is interference. So we have learned about the superposition of waves in chapter 6. Okay, so in chapter 6 we have seen all these terms, but this is about light we have to consider. According to this principle, when two or more waves overlap, the resultant displacement of a particle of a medium at a given point is the sum of the displacements. So particle of medium at a given point, sum of the displacement of particles produced by individual waves, as if each wave is only one which is present. Because of this, particles in medium present where the crest or troughs of two waves coincide with will have larger displacement, while particles present where the crest of one wave coincide with the trough of other, displacement will be minimum. That is destructive interference that already we have seen. If amplitude of two waves are equal, then the first set of particles, the displacement will be twice the amplitude of the individual wave, and for the second set of particles, the displacement will be zero. Thus, the intensity of wave, which is proportional to the square of amplitude of wave, will be non-uniform, being larger at some places and smaller at others. This is called interference. Interference is shown in figure 7.9 for water waves. S1 and S2 are the two sources of water waves of the same wavelength and amplitude and are in phase with each other, that is, okay, at any given instant of time. So if you want to see, you can see here also this diagram. S1 and S2 be the two sources of water waves at same wavelength and amplitude and are in same phase with each other. That is, at any given instant of time, the phases of waves emitted by both sources are equal. The crests are shown by continuous circles while the troughs are shown by dashed circles. Points where the crest of one wave coincides with the crest of another wave, where the trough of one wave coincides with the trough of another wave by blue dots. At these points, the displacement is maximum and is the twice that of for each wave. These are the points of constructive interference. The points where the crest of one wave is coincide with the trough of another wave shown by the red dots, and at this point displacement is zero. These are the points of destructive interference, and thus along the some straight lines radially diverging from the midpoints of S1 and S2, there is a constructive, that is along the radial lines connecting the blue dots, and destructive along the radial lines connecting the red dots interference. So interference had been observed in case of water waves and sound waves. It was observed for light waves in the laboratory for the first time by Thomas Young in the year of 1801. As noted above, this was the first group of wave nature of light, and we will discuss below. So on the basis of that, we have to discuss coherent sources, okay, and by using Young's double slit experiment we can prove it. So that we will see in next lecture. Thank you, students.